I'm sure you can all relate to this image in some way, can't you? Imagine it's the middle of the night, you're fast asleep in bed, suddenly your pager goes off. And some of you probably have a really deep emotional response to this, don't you? Maybe for some of you, it's anger. Why is my pager going off at this time in the morning? Why is the system chosen to broke now? Maybe for some of you, it's excitement, because now it's your chance to go and be a hero. Yeah, I'm sure it's anger for most of you, isn't it? Now, whatever system you're working with, however you're choosing to build your system, I'm sure you've all been there when you receive a page, you get up, you go and sit in front of your laptop, and you can't for the life of you work out what it is that has caused your system to break. Who's been there where you've been command F'ing through a big wall of log files trying to work out exactly? Yep, quite a few hands. You've all been there. You can all relate. This is difficult, right? It's a difficult thing to do. This got even more difficult when we all started building distributed systems. Now, instead of looking at this log file on a single machine, you've got lots of log files across lots of different servers across an entire cloud provider. Maybe you don't even have servers at all. Maybe you've just got managed services that are just emitting logs, emitting traces. This got even more difficult when you decided you wanted to build an event-driven system. Maybe you read some articles online, you came to conference talks like this one, and you thought, yeah, event-driven architecture. That must be the only way to build scalable and resilient systems in the cloud. So off you went, you built your event-driven system, you prioritized asynchronous communication, and now you're sat there at 3 o'clock in the morning wondering, what happened to my system? Why is it not working? And that's what I want to help you with in this talk. I'm going to talk to you about what it is that makes observability so difficult in asynchronous systems, and then give you some practical things that you can take away and use in your systems. I'm James Eastham. I'm a serverless developer advocate at Datadog, but don't worry, this is not a talk about Datadog. This is not a talk about a specific technology, a specific SaaS provider. This is a talk about observability. And if any of you have heard me talk before, you'll know that there's one thing I love talking about almost as much as event-driven architecture. That is, of course, pizza. Who here loves pizza, by the way? Quick show of hands. Okay, those of you with your hands down? Really? Come on. So for the rest of this talk, you're all going to be developers for a completely fictional pizza delivery company called Plant-Based Pizza. Maybe it's the middle of the afternoon on a weekend, there's a big sporting event on, lots of people are trying to order pizzas, and for some reason the system's broken. And now you need to go and fix it. You need to go and observe it. And let's just get into a bit of history of the plant-based pizza system and how the system actually works. Once upon a time, life was an awful lot simpler. You had this single running process, a single database. Your system was reasonably easy to rationalize about. 2 moving parts, a server, a database. Nice and simple. But then you started to grow, you started to scale. I mean, why wouldn't you scale with pizzas that look like that, right? They look incredible. So you started to move to microservices. You started to build more distributed systems, all communicating synchronously, HTTP APIs everywhere. And this was okay for a while. And then you started to hit issues. You started to hit issues with the rate of change. You couldn't develop features fast enough. And that's because of how tightly coupled your system was. And of course, coupling isn't necessarily a bad thing. If you built a completely decoupled system, it will be really hard to get any meaningful work done. Event-driven systems aren't decoupled systems, they're simply loosely coupled systems. And this points towards one of the really core ideas in any modern software architecture, that you should aim for high cohesion and low coupling. Now, cohesion is one you've already kind of solved. The things that need to change together should live together. Microservices kind of gives you that. You've got these small, independently deployable units of code. Coupling, however, coupling's a lot more nuanced. There's lots of different types of coupling, and you want to try and reduce this coupling as much as possible. So that's led you to where you are today with your pizza restaurant. You've built event-driven microservices, all your inter-service communication happens with events, and at a very high level, you've got 5 different services. Before we get into the observability of it, let's just have a look at how this system actually works. So someone comes to try and order a pizza, they're going to hit a create order request, which is going to hit the order processing service. The order service is going to go off and do some validation, maybe take some payments, whatever that might do, and then it's going to publish an order confirmed event. The order confirmed event is going to be consumed by the kitchen service, which is going to go off and actually prepare the pizza. That's going to publish an order prepared event, which is then going to be consumed by the delivery service. The delivery service goes off and obviously delivers the order. Throughout all of that, the order service is also responding to these events to then be able to update the status of the order so that when you're sat there furiously refreshing your app, you understand what the status of the order is. So that's the high level of the system that you want to observe, that you want to work through. Now, before we get into the actual observability stuff, I think language is such an important thing in human life in general, really. The words we use, the terms we use are really, really important, even more so when building something as complex as distributed systems. So let's just agree on some terminology. What exactly is an event? If we're building an event-driven system, this kind of makes sense to understand, right? An event is an immutable fact. It's something that has happened in the past. It is something that cannot be changed. Imagine it's the middle of the night, you're in your house, you need to get up and you need to do something. Maybe you want to go and get a snack, maybe you need to go to the bathroom, whatever that might be. You get up in your house, you're going to move in your house, and you're going to hit a light switch. That's going to raise a light switched on event. It is irrefutable that the light has been switched on. You cannot unswitch on a light. The light is now on. Once you finish doing the things that you're doing in the room, you're going to hit that light switch again. That's going to raise a light switched off event. The light switched off, the light switched off. These things happened. It is irrefutable. They cannot be changed. So if that's an event, what does it mean to be event-driven? And I think this sometimes gets confused a little bit with what I'd call an event-based system. So event-driven systems and event-based systems both trigger functionality using events. The difference with an event-driven system is that an event-driven system triggers business functionality with business events. Events are not a new thing in software development. I started out my career building Windows Forms applications in .NET. In a Windows Forms application, you can do things when a button is clicked, when a mouse is hovered, when the window gets resized. Even in more modern ways of building software, if I upload a file to an S3 bucket, that's going to raise an S3 object created event. These are technical events. These are not business events. Business events are things like order placed, pizza boxed, order delivered. You could look at two different businesses in the exact same domain, and they would probably have a different set of business events. They're probably all clicking buttons, uploading files, hovering mice. And often when you hear about event-driven systems, you might also hear about message-driven systems. Are you doing events or are you doing messages? And what is the difference between the two? Well, actually, events are just a type of message. And there's three different types of messages you will often see: commands, events, and queries. Now, commands and events are very similar. The difference is mostly just a statement of intent. Am I telling a system to do something, or am I reacting to something that has happened in a system? And then, of course, queries. Queries are me just asking for a piece of data. I want to get this specific piece of information from a system. So event-driven systems are message-driven systems. And then inside events, you have lots of different types of events. Two of the most common types of events that you will see are notification events, thinner events. These are really lightweight, really slim pieces of data. Maybe it's an order confirmed event and it only has an order ID. Nice and slim, just a notification. And then you've got event carried state transfer, or thicker events. Now, event carried state transfer is where you carry the entire state of the entity as part of the event. Typically a lot more data in event carried state transfer. And these events always pass around, typically with these three high-level components. You've got producers, you've got consumers, and you've got some kind of message channel in the middle. Here, this is labeled as an event bus. This could equally be a queue, a topic, a stream. There's just some kind of message transport in the middle. Producers and consumers have no direct communication with each other. All of the communication is asynchronous. All of the communication is through some kind of message channel. The primary integration pattern at work here is the publish-subscribe integration pattern. Producers publish events and n number of consumers can subscribe to these events. And you have very different responsibilities as a producer or a consumer. As a producer, your main responsibility is to stick to the schema that you agreed on, stick to the structure of the event. Try to avoid making breaking changes, try to ensure that you have backwards compatibility at all times. But there's some really interesting things that you're no longer responsible for. You're no longer responsible for how people use your events. You publish an event, consumers might use it, they might not. When compared with synchronous systems, though, it gets really interesting because now you're no longer concerned with the constraints of the system downstream from you. If you imagine you're building a system that makes synchronous API calls, you need to care about where that service you're calling is. You need to care about how much throughput it can handle. You need to care about its uptime. Is it responding fast? Is it responding slow? These are all your responsibilities as a developer of the system that you then need to call. With an event-driven system, that's no longer your responsibility. That's the responsibility of the consumers. It's the consumer's responsibility to control and plan for the ingestion rate, to control and plan for the events that they receive. The same way you would if you were building a synchronous API, you would have some kind of rate limiter in place. The same would apply for an event-driven system. You want to control the ingestion, plan for ingestion, plan for changes. So that level sets us on events and event-driven architecture. So what about observability then? This has become quite a lauded term a little bit in recent times. Observability, what does it even mean? And almost any conversation ever about observability talked about the 3 pillars of observability, which are logs, metrics, and traces. But I think this misses the bigger picture, because logs, metrics, and traces are the how you would implement observability, the what of observability. But it misses the why. Why is observability so important? Why should you care about logs, metrics, and traces? An observable system should allow you to ask questions of your system you didn't know you needed to ask from a place that is external to your system. Quite a strange way of putting it, isn't it? Asking questions you didn't know you needed to ask. What does that even mean? Let's imagine a scenario. Imagine your page has just gone off and there's an issue with your system. And that issue, for an argument's sake, happens to be that the database has gone offline in the order service. You get up, you diagnose the issue, maybe you realize that the database has run out of disk space. So you're going to fix the issue, you're going to increase the disk space, whatever it might be. And then you're going to put something in place to make sure that doesn't happen again. Maybe you put a metric in place. Maybe you put an alert in place. You're going to do something to monitor the disk space of your database so the same issue doesn't happen again. Now, once you do that, the chances of that same issue happening again are pretty unlikely because now you're monitoring for it. Now you're alerting for it. Distributed systems, though, fail in new and novel ways all the time. With distributed systems, you're dealing with unknown unknowns. You've got lots of different systems being developed by lots of different people with different SLAs, different release cycles, different priorities. Things are constantly changing. There's no way you can predict ahead of time exactly how a system is going to fail. So this ability to ask questions of your system helps negate some of these challenges. These things get even more complex, though, when you start building asynchronous systems, event-driven systems. Not only are you now dealing with systems that are constantly evolving and constantly changing, they're also communicating completely asynchronously. This is all a form of complexity. All software systems are complex. It just depends what type of complexity you're dealing with. Essential complexity is the complexity that's inherent to the business domain you're operating in. You can't get rid of essential complexity, whether you're using monoliths or microservices or Kubernetes or serverless, it doesn't matter. Essential complexity is always going to be there. Accidental complexity, though, you have some control over. This is the complexity that comes from the decisions you choose to make. Monoliths, microservices, event-driven architectures, serverless, all of these have their own types of complexity. And if you think back to that simpler time, I'd argue this system has a lower accidental complexity than one that uses microservices. It's a lot more easy to reason about. If something goes wrong, I know I need to look at the application or the database. There's 2 moving parts. And of course, this works up to a given point, and then as you start to expand, you start to add all of these different components, all of these different processes. Event-driven microservices might simplify things like deployability, allowing teams to work and operate independently. But it does make things like observability more complex. You've got a lot more moving parts. You've got a lot more things you need to reason about and understand to understand how your system works as a whole. Cause and effect is incredibly difficult in an asynchronous system. If you think about a synchronous system, you've got the order service making a call to the kitchen service. It's reasonably easy to reason that the order service is having an effect on the kitchen service. As a developer of the order service, you know the DNS name of the kitchen service. You're going to make a call to that service, and you're going to get something back. It might be an error code, it might be a success code, it might just completely time out. You could even follow the bytes across the network, but you can understand that one system is having an effect on the other system. Whereas if you compare that to an asynchronous system, it is really difficult to understand when you publish an event, who is using that event? What effect is you publishing that event having on the rest of the system? And equally, if you're consuming events, how do you understand exactly what's happening upstream of you? So the most important part of observability in an event-driven system is distributed tracing. The most important of the three pillars. And to settle on some terminology, this top-level thing you're seeing here is a trace. A trace is the end-to-end flow of a request. Inside a trace, you will typically have lots and lots of different spans. And these spans can span multiple different back-end systems. Spans can also have attributes or tags, and this is what will add context to your system. This is what will give you that ability to ask questions of your system that you didn't know you needed to ask. Let's see this in action with one of the commonly touted benefits of event-driven architecture, evolvability. If you build an event-driven system, you're evolvable, aren't you? You're evolutionary. You can make change really easily over time. And let's think about this specific part of the architecture here. You've got the order service publishing an order confirmed event, and the kitchen service is consuming that. So the kitchen service is going to consume that order confirmed event, and then it's actually a notification event. It's a thin event. So the kitchen service is going to say, well, I don't know what to do with this order. I don't know what I need to cook. I'm going to make a call back to the order processing service to get more information about this order. And then because you're evolvable, because you're building an event-driven system, well, maybe another system pops up that's also consuming that order confirmed event that also needs to call back and get more information. And then 3 more services appear. And then another one, another 3, and then before you know it, your entire system is on fire. Because all these systems you didn't even know existed have evolved and started making calls back to your system from that simple thing of you just publishing your order confirmed event. Now you need to deal with all this load coming back. A core principle you'll often hear with EDA is that services are unaware of the downstream consumers of their events. And whilst this is technically true, it can be a really dangerous statement because although you're not aware with what they're doing with their events, you should probably be a little bit interested in what effect that might have on your system. Observability can give you that. Distributed tracing can give you that. If you have good distributed tracing in place, you can go and have a look at that original API request that hits your API, that create order. And then you can follow that trace all the way through and you can see that another system has consumed your event and then made a call back to your service. You can now directly correlate that event that you published back to a request that came back into your system. You understand the cause and effect. You understand the effect of your event being published. So you look at this and you think, well, we've got a solution here, don't we? We're publishing notification events today. We're publishing thin events. Let's start publishing thicker events. Let's start including more data in our events. And as you expect, you roll out this new structure of event, you roll out this new version of your event, and suddenly the calls back to your system stop. They minimize because obviously teams no longer need to make the call back because they've got all the information they need in this event. Fantastic, celebrate. We're done, right? We've evolved our system. We've evolved it using our observability data, and we've made an informed decision about our system. So now you're full of confidence, aren't you? You've made a change to your system once, you've evolved your event structure once, and now you have another change to make. Now you have another requirement. You need to start supporting multiple currencies. So today you're publishing the order value just as a decimal, as a number. But you think, wow, we've changed this schema once, let's just go and change it again. Let's, instead of publishing the order value as a decimal, let's publish it as an object. Let's start including a value and a string. Who can see an issue with that change, potentially? Yeah. Because although you might think, well, it's just the kitchen that cares about this order confirmed event. It's just the kitchen, and the kitchen only cares about the items on the order. They don't care about the value. But remember, event-driven systems are evolvable. So an analytics service has appeared that you didn't even know existed. The analytics service really, really cares about the order value. And now you've just broken a system that you didn't even know existed. Not particularly evolvable, right? It's also not a very good way to make friends, believe me. So what can you do now? How can you deal with this now? And observability is your friend again here. And if there's one thing you take away from this talk, this is it. The schema you use in your events can be your enemy, but it can also be your friend. Whatever you do, adopt some kind of defined specification for your events. The Cloud Events specification is one such spec. This is a spec for defining what you should include in your events. And there's a few different properties here. The data property is the actual payload of your event. This is the actual contents of the event. Of course, this is going to be different for the different types of event in your system. You've got the data content type. This is what type of data is inside that data property. Here it's JSON, it could be XML, it could be binary, whatever that might be. You've got the time. This is the time the event was published. And the ID. This is a uniquely generated identifier added at the point of publish. This will allow downstream consumers to implement things like idempotency, to understand, have I seen this event before? Yes, I have. I can safely ignore it. And then really importantly for this conversation around evolvability, you've got the source and the type up at the top. This event came from the production order system, and it is the order created event. And it's version 1 of that order created event. Really importantly, you've got the version number in there. And then finally, there's one field I skipped over here, which is the trace parent. This is part of the Cloud Event specification to actually include distributed tracing inside your events. This is what gives you the potential to be able to understand cause and effect. Here, this is using a W3C trace context. This could equally just be a correlation ID, just some common identifier you pass from system to system to system. But if you're adopting the Cloud Event specification anyway, it kind of makes sense to adopt some other standards. So this really long, complicated string is actually broken down into 4 unique parts. You've got the version at the start. This is the version of the trace context. There's only one version at the minute, so obviously it starts at 0. You've got the actual trace ID. This is the overarching trace ID that this event is part of. And then you've got the specific span that was active when this event was published. Finally, on the end, you've got a set of flags. This allows you to do things like sampling. You can indicate if this trace was sampled at the parent. If it was sampled at the parent, then you want to keep this trace in the downstream system. When you start to bring all of this together, you start to include this tracing information in your events. This is what gives you the ability to understand cause and effect. Because when this system publishes the event at this point here as part of this span, you're including all of that information, which allows the downstream systems to then understand what caused them to run. OpenTelemetry also publishes a set of conventions. They call them the semantic conventions for messaging, which I'm going to shorten to best practices because that's a little bit of a mouthful. This defines a set of tags that all spans relating to messaging should include. Things like the operation name. Am I sending a message? Am I receiving a message? Am I processing a message? The messaging system that you're using, what is the transport layer? Is it SQS? Is it EventBridge? Is it Kafka? Is it Kinesis? And then finally, the destination name. What is the name of the thing I'm publishing to or consuming from? This is the name of the queue. It could be the name of the topic, the name of the event bus. And then I've added a couple of additional ones here that I think that I've found are really, really useful. So to include in your tracing, in the context of that specific trace, the version of the message that was published and the type of message that was published. This then gives you the ability to ask the questions of your system to understand who the downstream dependencies are. Because now you can look at this situation you're in. You can look at needing to change the schema of your event. And today you're publishing version 1. And when you need to make that breaking change, you're going to start publishing version 2 as well. So now you're publishing both version 1 and version 2 of your event. And because you've got this context in your observability, you can go and ask the questions of your observability backend and actually understand who is dependent on this version of the event, who is dependent on version 1 of the event. That then allows you to go and talk to other teams, to go and collaborate and understand when teams can switch over to version 2, eventually allowing you to depreciate version 1. I realise I make that sound incredibly simple. It can be more complicated than that, but having the data there in the first place allows you to ask these questions to get this understanding of your system. So another related point to observability is how you document your event-driven systems. Evolvability can cause you a lot of challenges. How you develop your system over time, how you change the schemas of your event over time is really quite important to building a successful system. Who here is familiar with the idea of API-first design? Okay, a few hands. Okay. If you're not familiar, the idea of API-first design is that the first thing you do when you start building a system is design the API. Imagine you've got a front-end team and a back-end team. Before you write a single line of code, you're going to agree what the API contract is between these two systems. Then when it comes to integrating them together, in theory, it should be nice and simple. And as Dave kind of alluded to in the keynote, when you're building an event-driven system, your events are your API, which means you should really practice event-first design. The events you publish are the API of your system. Treat them with the same respect you would treat an actual API. Think about versioning. Think about the schema. Think about how you expose your internal domain model externally to other systems. And then document it. Tell people about it. And I wanted to say a quick word on Event Catalog. If you're not aware of Event Catalog, it's an open source project from Dave Boyne. And it's a way to make it really easy to document and discover your event-driven systems. You can load in defined specifications and you can look at how your system links together. You can make it discoverable. Now, at the moment, Event Catalog requires you to upload documentation files, things like async API specifications. But on the roadmap, there's plugin integrations coming for lots of different message brokers, which is going to allow you to build, hopefully, some kind of self-documenting event-driven system. And I think there's something really interesting there in this idea of a self-documenting event-driven system. Because you've got these events actually flowing around, don't you? The events are actually happening. They're triggering business functionality. And who here has ever released a feature, released something, and forgot to update the documentation? Don't worry, it's a safe space. No one's going to shout at you for not doing it. It's hard, isn't it? It's hard to keep things up to date. It's hard to remember to do it. Sometimes we just forget. Sometimes, frankly, we just can't be bothered. Documentation is hard. So we've got these events flying around. Why can't we make our event-driven systems self-documenting? So this is what you start to do. You start to actually, in your consumers, in your producers, you start to actually log the contents of the events. You start to actually store the content of the events as context against your traces. Seems simple, right? Now you've got this ability to go and look in your observability system and look at the actual events flying around. And if you do this, somebody, somewhere in your company, probably a security person, is going to have a minor heart attack. Because now you've just potentially exposed PII or sensitive information into your observability backend. Probably not something you really want to do. But there's still something interesting here. You want to be able to understand the events in your system. You want to be able to understand the events that are flying around. But equally, you want to be careful about the data you expose. So a practice I'm a really big fan of is, instead of storing the contents of the event, store the schema of the event you publish and receive in your observability system. Most programming languages will have a package or something you can include that will allow you to extract the schema of an event from an actual JSON string. This example is in .NET. You can do this in other languages as well. So instead of storing the event data itself, you're actually going to log the schema. You're going to add the schema of the event you receive to the context of the trace. That allows you to start to play detective, to allow you to start to ask these questions of your system, the questions that you didn't know you needed to ask previously. It's context you add to your spans that really makes distributed tracing start to be powerful. Imagine if you get a call off someone on your support team and there's an order that's gone missing. Order number 12345. They've not received their pizza. Panic. Now you have the ability to go into your observability backend and actually run a query across your entire system to say, give me all of the requests related to this specific order. And then you can start to understand exactly whereabouts in your system that order is. It's tracing in distributed systems that allows you to start to understand this cause and effect. Tracing isn't a silver bullet though. It's not as simple as you might initially think. Here's an example of a full end-to-end distributed trace from inside the pizza restaurant. Each different color on this graph is a different back-end service. And you can see there's a lot of them. There's a lot of different back-end services here to make a pizza. And you might think, well, this is really useful, isn't it? I can zoom in, I can go and have a look at a specific trace, I can have a look at a specific span. I can actually see that this specific event spent 294 milliseconds inside an event bus, dev.orders. It then spent 100-ish milliseconds inside an SQS queue, and then it was picked up and processed by a downstream system, by a Lambda function, this may be. Sounds really useful, doesn't it? Being able to actually see exactly which message channels, exactly how long your event spent in each individual message channel. Now, of course, to get this kind of observability, this is, in a lot of cases, going to require a little bit of work on your end, because you're going to need to add these spans for how long your event spent in a given message channel. And most event payloads you will see will give you the capability to do this. Take this sample event from SQS. If you're processing SQS messages, this is what the structure of a message will look like. And you've got this sent timestamp attribute. This is the time in which SQS received this message. So you can use this information to actually infer the length of that span, to infer the length of the amount of time that this event spent inside SQS. And then when you actually go and consume this event, because you've propagated that trace context, because you've included that trace parent in your specification, you can write code like this that then extracts that trace information from the inbound event and continues the trace downstream. You can start a new span in your downstream system and say the context of this span is the one that comes from the upstream system. Looking at this screenshot again though, you can see that there's these really two long purple lines that take a disproportionate amount of time in the middle. In this specific example, this is a workflow that starts. This workflow needs to go and do some other things. It takes a disproportionately long amount of time relative to the rest of the trace. And many of you are going to end up in situations like this. There'll be an event that happens somewhere in your system, and then there's going to be some kind of long-running business process that happens. And business processes can take seconds, minutes, hours, weeks even. And a lot of business processes have a lot of time where nothing is actually happening. If you think about making a pizza, you're going to put a pizza in the oven and you're going to sit there waiting for n number of minutes, depending how hot your oven is, for that pizza to be cooked. There's a lot of this non-time, this empty time. Take another example. Imagine once a day, you need to run a reconciliation process across all the orders that were confirmed that day. And it's more efficient for you to do this as a one-off process at the end of the day, as opposed to doing it piece by piece as an event comes in. If you were to propagate this trace context into your daily job, your daily analysis job, all the observability for your daily job is going to end up in the traces for the actual event being published, the order confirmed event. And in some cases, if someone had ordered a pizza at maybe 10 o'clock in the morning, which sounds like a wonderful thing to have to breakfast, You've then got this really long trace. You've got this 14-hour trace going on with a lot of empty time in the middle, and then suddenly this daily job runs at the end of the day. So you don't want your daily job to appear under each individual upstream trace, but you do still want to understand cause and effect. You do want to understand what caused that event to get into the place ready to be processed. So this is where span linking gets really useful. Instead of propagating the entire trace to a downstream system, instead you can link the span in one trace to a span in another trace. This keeps things independent. You've now got a separate trace for your downstream system, for your daily job, and you've got separate traces for your upstream system. And when you're processing the individual message in your daily job, you can link that back to the specific trace that happened upstream. Which then begs the question, doesn't it? What's the right thing to do? Do I propagate the trace? Do I link my spans together using span links? What's the right one to choose? And the simplest way to think about that is this idea of a unit of work. What is the unit of work that you want to observe? What's the useful thing for you as a developer? What's the business process that you're trying to add observability to? That might be the daily job as a whole. So inside the daily job, you probably want to propagate traces between systems. Maybe your create order request comes into the pizza restaurant, you raise the order confirmed event, and you want to know that the kitchen service consumes that event. So maybe you propagate the trace in that context, but then the actual internals of the kitchen, the actual internals of the workflow to make the pizza, maybe that is a span link instead of propagating the trace. Both things are incredibly useful. The important thing to take away is make sure you keep these links, because having these links, having this end-to-end trace is what allows you to understand your dependencies. You can now understand that the API in your system that manages products, that manages pizzas, has an upstream dependency on a pricing service, on some kind of service that manages prices. You can also understand that there's systems downstream of you that have a dependency on you. There's these downstream systems that are using your events. You also downstream dependencies on things like DynamoDB, on SNS. Having this distributed tracing in place allows you to understand cause and effect. It adds the required nuance to this statement. Because although you don't really care what downstream systems are doing with your event, it certainly helps to understand who is dependent on you and who you are depending on. So we've talked a lot about distributed tracing up to now, but remember there's 3 pillars. There's not just one pillar. So metrics. Are metrics still valuable in a modern observability strategy? And metrics are still useful because metrics can give you this macro level view. They can give you this high level view of your system as a whole, of how your entire system is functioning. OpenTelemetry also publish some best practices, they do call them semantic conventions, but that's really hard to say, about what metrics you should care about in a message-driven system or an event-driven system. And then I've added a couple of my own here as well. So queue depth. How many messages are building up in your queue? This could identify a bottleneck in your system. This could identify that your system can't keep up with the throughput. If this is a dead letter queue, this could also identify a problem if you've got messages building up in a queue. You've got the count of messages being published and consumed, but also the size of the messages being published and consumed. This allows you both to understand throughput, but if you have a sudden drop-off in the size of the message or a sudden increase in the size of the message, that could also potentially point towards a problem. You've got the age of the message. How old is the last message that you processed? If this metric is increasing, that can again point towards there being some kind of bottleneck in your system. If you're starting to process messages that are older and older and older. The in-flight latency, if you're building a latency-sensitive system, this can be a useful one to understand. Is the message transport you've chosen fast enough for you? Error count, an obvious one. How many errors are happening in your system? And then finally, what I think is a really useful one is the count of a type of message that you're seeing. How many order confirmed events have you seen? How many payment failed events have you seen? How many payment processed events have you seen? This is both useful for you as a developer to understand if your system is working, but also useful for the wider business. You're now starting to add value to the business, to add this kind of data that you can get from these business events that are actually flying around. Which of these metrics you choose to alert on really is going to be different based on your specific context. Maybe end-to-end latency is really important to you. Okay, alert on that. Maybe the size of the messages. Maybe you're really sensitive to the payload size. Maybe you're really close to hitting service limits in some of the AWS services. Okay, understanding the size of the message you publish and how that changes over time is going to be a really useful one for you. Another really important thing is that success is also an important metric. If your system processes 10 messages a minute on average, 20 messages a minute, if that metric suddenly drops to 0 and you suddenly stop processing any messages, there might not necessarily be any errors, but that could still point towards a bigger issue inside your system, point towards something actually going wrong. So now that you've got all these things in place, let's actually walk through what that could actually look like. Because remember, you're still sat there middle of the afternoon, your page has just gone off, and you're trying to now work out what exactly has gone wrong in your system. So you go and have a look at your observability backend, and you realize that actually there's an increased error count. That's what caused your pager to go off. This high-level view, this macro view of your system has told you that there's an increased error count, and there's an increased error count inside the kitchen service. So you can go into your observability backend, and you can start to ask questions of your system. The first quite obvious question you're going to ask is, show me all of the traces that have an error. Show me all the things that are going wrong. And because you're adding this context to your traces, and errors are a type of context, you can now see all the traces that have a problem really quickly. You can then, because these give you this really micro view, this really granular view of a request, you can dive into an individual trace, a trace that has an error, and say, okay, what's actually gone wrong with this trace, with this request? You can see the message was retried 3 times. You've got some kind of retries in place. But you've also got this trace propagation. You've got this ability to be able to look upstream and see exactly what caused your system to execute, what caused your system to run. So you double click into that. You think, okay, well, let's actually have a look. We're building an event-driven system. Let's actually have a look what the events look like. Inside your same UI now, you can look at the schema of the event that caused your system to execute. You've not had to context switch to another tool. You're still inside your observability system. And you can see, because you've got that trace propagation, here is the structure of the event that was published. Here's the structure of the event that I received. And you think, this is weird. A few weeks ago, we started publishing thicker events. We started including more context. It looks like there's been a regression of some kind in the upstream system. But to check yourself, you take this schema out of your observability system and you drop it into your test suite. You drop it into your unit tests, and you run your tests against this specific schema of the event, this specific structure of event. Lo and behold, your system fails. You're expecting a property in the event that isn't there. You've now had that ability to go and play detective, to actually understand what has exactly happened in your system, what has caused your system to run, and use that to quickly diagnose the issue. Now, I realize that was a pretty trivial example that I've just walked through. What I hope that identifies, though, is that having this ability to ask questions of your system, to understand cause and effect, is what will really help you understand your event-driven systems. If you're building a new feature, a new functionality, a new service, ask yourself the question, how will I understand what caused my system to execute? How will I understand what caused my system to run, to do some work, to do something? And then use context to be able to ask questions of your system. Add the context to these traces that you can then run queries on. You can use to understand your system. You can use to correlate. Maybe you have a set of errors that are all related to the same customer ID, the same order ID, the same user ID. Because you've got all this information in your traces, you can start to correlate things that are causing problems. And then think about things both at the micro level, at an individual request level, traces, logs, to understand a specific request in your system. But also, don't forget about the bigger picture. Don't forget about the macro view. Having this high-level look at your entire system as a whole will give you that ability to be able to alert and do things like that. Most importantly, think about how you can get this into your day-to-day work. A company I used to work for, we used to have, as part of the pull request template, whenever you wanted to merge a change, to do something new, you had to answer the question in the template, how will I know that this specific piece of code has made it to production? And that might just be a 3-line code change. You still had to answer the question, how would I know that this code is in production? And if you constantly ask yourself that question as you're developing, how will I know that the code I'm changing is in production? You will always have the observability you need to understand if your system is working or not. Now, this is the first time I've actually given this talk, so any feedback you have, both you can give to me now or up at the front, or I'd really appreciate any feedback in the app. The slides for the talk are available on these QR codes. I also have a whole bunch of content on my YouTube channel. And actually, the top QR code will give you a link to Plant-Based Pizza. This is an application you can actually go and see, you can actually go and deploy, and I've just lost my audio. Ah, there we go, we're back. This is actually an application you can go and build, you can go and deploy, you can actually go and have a look at that. So I gave this talks like this a few times, and people were constantly asking me about real-world examples, so I actually went and built it. So you can go and have a look at that as well. Thank you all very much for listening. I hope you enjoy the rest of your day. Thank you.